Today I have the honor to present Dr. Mikolaj Czerkawski. He's a researcher focused on AI, computer vision, signal processing, and Earth observation. Former postdoctoral researcher at European Space Agency and now co-founder of Asterisk Labs and Major Tom, a collaborative platform designed to support reuse of Earth observation datasets within AI pipelines. The stage is yours, Miko.
Thanks. Hi, everyone. Thank you for being here, and thank you to the entire AI ES team for making this event possible. Thank you to the AV staff as well, and the entire technical staff that makes this event possible. Thank you for the patience of listening for 6 hours about AI and environment. Without further ado, I'm going to briefly introduce myself. My name is Miko. I'm one of the co-founders of Asterisk Labs. And the title of this lecture, which is on the evolutions of EO spheres. And now, the story is, a few months ago, I was asked to give my talk a title, and I struggled considerably just because of how many topics I wanted to cover. And they're all sort of related, but there's not a single sequence that delivers a clear narrative with a clear title. So I just came up with something that I hoped sounded cool enough. Right, and obviously that has some nice references that reflect my namesake, Mikolaj Kopernik. To many of you may be known as Nicolaus Copernicus. And my favorite, and I suppose everyone's favorite Earth observation program, the Copernicus program. Anyway, I could have made it more focused with a slightly more controversial title, What's Wrong with EO? Or a more positive title with Joint Stewardship of Earth Data Commons, which is something we are very, very much passionate about at Asterisk Labs. But just for the sake of simplicity, I stuck to on the evolutions of EO spheres. And I could have made it maybe sound a little more profound, like Copernicus, using Latin. And basically, what some of you might recognize, the title very much reflects a work from a few centuries ago that was quite revolutionary, unlike this talk, on the revolutions of the heavenly spheres. Right? Now, a major downside of Copernicus' work is that it had no images from space, not a single one. And this talk will have a few of them, so there's that. So first, I would just want to give a very quick overview of the history of observation. I think that history actually goes many, many centuries before, depending on what you interpret as Earth observation. Now, my question is if anyone recognizes the platform that this was taken from. A pigeon, correct. A pigeon, a very early instrument for Earth observation. However, now largely obsolete just because of how unpredictable orbits of pigeons are. Now, since then, we have moved quite significantly, and now my question is if anyone recognizes this image and what's in the image. Any guesses? It's our current location, Earth. It's one of the first images taken from Earth's orbit of Earth, and it looks quite crap. It was taken by NASA Explorer 6, but it then allowed us to iterate more and more on the technology, and obviously now we are all aware of the richness of the Earth archives. And this is our current location, I think from a few years ago, actually. You can see the airfield, and this is where we are currently. This is Sentinel-2 L1C, combined with L2A, and these images actually come from Major Tom, which I will cover later on. There's Sentinel-1, there's the digital elevation model. Yeah, here it is. So by now, we have moved on to a new landscape where we have a lot of images of Earth, unlike Copernicus, and we actually might struggle with processing of them. There's something wrong with the layout, but I think that should be fine. So basically, I think what this talk should cover as well is what drives ZO, and it's these two things, data and community, and I hope the layout of the next slides will be improved. And likewise, these might be the two components that we want to focus on and that might need to evolve in the next couple of years. So first, a quick story, and I will connect that story to several technical works we've been doing in the last couple of years and what I think will be quite relevant in the next couple of years, and also to the story of Asterisk Labs, which I think is quite exciting, at least to me. So my background is not actually Earth observation or remote sensing. I actually started my PhD with radar signal processing, and I hadn't looked at a single Earth observation image in my work until maybe halfway through my PhD. But I always knew I wanted to work more with images, right? So there was this project that had to do with monitoring crop yields in Scotland. And a major obstacle in Scotland, as some of you might be aware, are clouds. So my supervisor asked me to maybe look at a few techniques that could allow us to approximate the reflectance behind the thick clouds so that they could later do something else within the crop yield monitoring project. And crop yield monitoring, as exciting as that sounds, wasn't something I felt particularly passionate about, but I knew I liked looking at Earth from space. And this image is one example from my PhD work, where basically what I try to do is using and exploring different ways of transferring information from the image or from a large data set of images to estimate the reflectance. I've briefly worked on simulating clouds as well, so that we could evaluate them better and get an idea of how well these models are performing, because obviously, if we have a cloudy image, there's not really a way, at least now, to get proper ground truth. Right? That was just a quick overview how I ended up in Earth observation. But now, a major spoiler alert, clouds are actually quite cool. And I stopped removing them. I am healed. Just look at that. I took that picture about a week ago. Oops. Wait, there's two of these, and each of them is quite random. Hold on. Here it is. I took that about a week ago, and it's just an illustration of how amazing clouds are, including the clouds in satellite images. So I'll cover that later, because that's one of the founding principles of Asterisk Labs, really. Anyway, another spoiler, generative models have improved. So I used fairly simple methods back then to estimate the reflectance behind the cloud. And by now we have a set of works that use generative modeling for much more interesting tasks than cloud removal. So this method that we developed still during my time at the European Space Agency still, that basically allows you to transfer between and translate between text captions and 2.5D terrain representations using Sentinel-2 data, actually, and the Copernicus DEM model. There's another one called CopGem, very much similar to Terramind, which is also an instance of a generative model using Copernicus data. This one's fully based on diffusion, but it's using a transformer architecture that allows you to actually extrapolate to more modalities quite flexibly when it comes to the architectural design. It's quite fun. There's demos for both of these models, so you can actually plug them in and see in your browser how they work. But it's just one quick sneak peek to what actually happens once we have access to large-scale Earth observation data that's easy to integrate into AI workflows, right? So this couldn't be built before, and that brings me back to what I've done during my fellowship at ESA. I was actually asked to, I joined the team to be the expert for generative AI, and that made sense because back then I also worked on some open source courses for learning about diffusion models and so on. So the idea was we should do something about that within the European Space Agency field lab, right? Now, a major obstacle back then was that there wasn't a whole amount of AI-ready datasets available. There were some produced by groups that the members of whom are present here. So there was already some activity in this area, but nowhere near the level that I wanted to, that is often needed for developing new large-scale models. So I actually very quickly turned to working more on data-centric analysis, and which eventually led us to Major Tom, which I will cover in one more minute. In any case, I started working quite a lot with representations from existing models on existing data. So one of the early works back then was looking at the CLIP representations to see whether we could detect cloud presence, and that was basically reusing CLIP embeddings to see whether they can tell us something about cloud presence. Very simple work, but it actually performed quite decently. Now, the next thing I wanted to do is explore why the general-purpose generative AI models, like Stable Diffusion, that was released in, I think, 2022, so back then it still felt quite recent, why they perform good at all if they weren't trained on Earth observation-specific data sets. So again, that actually involved looking at the training data. In the case of Stable Diffusion, we had full access to the Lion 5B dataset, which contains 5 billion images taken from the web, combined with captions. Captions come from the ALT tag in the HTML element. So you can actually see that you can browse Lion 5B using CLIP embeddings. Again, this is a tool that was built by Lion 5B authors. So if you just type satellite image ROM, you actually get something that's quite decent. So what we did is we, again, used embeddings back then to filter 5 billion images to estimate how many of them might actually contain Earth observation data, right? So there were a few techniques and a few tricks that we used to filter that data, and I won't go into the detail here. But my main point is that there's quite a lot of Earth observation data available online, and similarly, the general-purpose model that you might interact with are very likely to have been trained on that data. With one specific context that's relevant here is that there's a very strong bias in those pre-training data sets towards things that humans will talk about online, right? So you can probably recognize the middle image in here. So these are the types of samples that models are trained on when they're not trained on Earth observation-specific data. It's interesting. It's an interesting way of looking at the representations of these models. In any case, I think what made me realize back then is that, we're looking at 5 billion images here. We're looking for an image that will give us a highest match with a satellite image of Rome or maybe a wildfire, and it usually worked. So the message usually is very clear. It's like when you scale up your data, it shines the brightest, right? So we don't really have an equivalent of Lion 5B, at least we still don't have that, I suppose, in Earth observation, right? But obviously, our archives of Sentinel-2 even contain tens of petabytes of data. And we're missing this one maybe layer that allows us to take full advantage of this data. And for obvious reasons, Earth observation data is very complex, quite hard to integrate into complex Earth workflows. It's definitely significantly harder than your usual JPEGs taken from the web, right? So that brings me to Major Tom, and I apologize to everyone who has already seen some slides about Major Tom. I will try to make it quick, but the main idea was to find some place where we could very quickly deliver a lot of Sentinel-2 data for pre-training so that I could maybe prototype some generative models during my fellowship, right? So again, a lot of design choices, like how do we actually create chips of the entire planet? How do we create multimodal chips? How do we deliver that to a large, easily for free and without the burden of logging in or registering anywhere to the wider community? So there's a set of design choices that we've made. The first one being the Major Tom grid, which basically allows us to have a set of points that allows us to define grid cells that should be covered by independent Major Tom datasets. So that basically allows us for this spontaneous capability to combine datasets that have been produced independently. So that's the Major Tom grid. And the idea is you take a data source of your interest. And obviously, this data source has to make sense for the 10-kilometer grid that we used, right? For some of the satellite or remote sensing sources that you want to work with, 10-kilometer grid might not be applicable, right? But for many applications that use Sentinel-2 and Sentinel-1, and that's obviously the significant majority of the works that we see out there, the 10-kilometer grid works quite well, actually, and gives you about 1,000 pixels of size on each side. So there's that. There's an app where you can basically browse Major Tom very quickly, and that just shows you that. I mean, that just shows you how easy it is to just pull the data that's already in this ready-to-use format that you can integrate into AI workflows. There is CDSC, but when you look at, Copernicus data space ecosystem, but when you go there, you actually look at these very large products that you might need to chip or realign and so on. And here, this is basically ready to go if you download the 70 terabytes of data that we produced there. But you can obviously subset that as well. So there's that. There's some amazing images. So one of the philosophies of Major Tom as well was to create a dataset that's fairly uniform. So it also has a lot of data that people don't yet care about. We actually try to cover every single point that's covered by Sentinel-2. So there's a lot of water bodies in Major Tom. There's a lot of uninteresting landscapes that to some people might be completely useless. But still, we thought, let's just take one sample of our planet and see what people want to use. And then the expansions came. So for some of the projects that we've done at PhilLab, we also went through the labor of creating expansions. And very often, there was always this nice effect of maybe one student building one expansion that could later be used in many other projects, right? So they would take the 3 or 4 weeks, or sometimes 6 or 8 weeks, maybe the majority of their stay at the PhilLab to build this data set, but then another student or another product could use it instantly. So here's an example of the digital elevation model expansion in Major Tom. So there's 4 image data sets right now out there. There's also quite a few embedding data sets that we've produced that allow us to quickly compare pre-computed model representations computed on the exact same data. So we have global coverage of embeddings that you can compare and you can benchmark your models on. More recently, I've also built a small subset of Major Tom with alpha-RF embeddings. It's only, I think, 60,000 or so grid cells, but it's in 10-meter resolution, and these embeddings are obviously right now of quite high interest in the community. And I mean, even the PCAs look amazing. But what's nice about this is that you can start prototyping and testing these embeddings immediately. Now, they basically represent an information from a whole year from multimodal representations. So it's a slightly different information content, but you can still do a little bit of experimentation with individual samples from the same year for Sentinel-2 and Sentinel-1, again, leveraging data that's already there. There's a few models that have since then been built on top of some of the Major Tom data, including Terramite, which was technically trained on TerraMesh, which contains Major Tom data, right? But there's also a few others, and there's this usual trend where Major Tom is very often used for prototyping as well, where you can just quickly plug and play. So what have I learned since then, after releasing Major Tom? Nothing. I already knew that cool models are cool sometimes, but data that drives them are always way cooler. So if you release data that's easily accessible to others, you might get a much more beneficial impact than releasing a model that you hope will solve everyone's problems. So one of the solutions for this type of evolution that I'm trying to highlight throughout this talk and a direction for Asterisk specifically is building large AI-ready data sets, and whatever AI-ready means, right? Now, Major Tom is one step in that direction. It's probably needs to be revised. The topic of AI readiness needs to be revised, and it's not yet clear whether Major Tom in a few months or in a few years, or even right now, it should be considered AI ready. But it's definitely easier to use Major Tom than spending 3 or 4 months building an equivalent data set using Copernicus infrastructure. Right, and then what? Once we have a nice landscape of AI-ready data that we can integrate into various workflows, well, the next part of the solution is staring at the clouds. And I'm going to explain more in the next slide, which basically brings me to what we've what we're most spending a lot of time on at Asterisk Labs. And that's our first project that actually lifted our lab off the ground, and that's Clouds Decoded. So if we go back to the Sentinel-2 missions that hopefully many of you are aware of, there's 13 bands. It's a sensor that's been designed for vegetation monitoring on land, right? But then, even within ESA, there's always this success story of Sentinel-2 being told about a sensor that's been designed for vegetation monitoring that's now being used for so many different applications, right? It's 10 meters, it's always 10 a.m. in Sentinel-2 locally. It's a 5-day repeat cycle. There are periods where we actually have lower repeat cycle with Sentinel-2C being used together with the existing platforms. And there's also a nice success story of the community basically pitching to ESA that the third satellite, the first satellite that was supposed to be deactivated should be maybe used in operations for at least some time to see what it would look like if we had 3 Sentinel-2 platforms operating at the same time. So I think in total, and this is probably from last year, so this might be outdated, but back then we had 36 petabytes of Sentinel-2 data, and 60% of that is covered by clouds. So very often for vegetation monitoring or anything else that has to do with land surface or earth surface, the data is simply, well, not discarded, but never used. It's ignored. It's 20 petabytes of data that no one gets to look at. That might have some useful information, right? So if we look at some examples of clouds in Sentinel-2, we have to admit that at least they're cool. And apart from that, they actually could bring quite a lot of scientific value. And that's what we're exploring in Sentinel-2. Because when we look at the ways that humans observe clouds, Sentinel-2 very conveniently aligns with an observation gap that we currently have. So we have satellites that operate at tens of kilometer scale. We have a kilometer scale sources. And then we have quite a lot of work that has to do with the micro scale, and that's mostly limited to very constrained settings. But when it comes to 10-meter scale, we don't really have much work to, much literature on covering that aspect. And one thing about clouds is that they are very complex, and they have you can observe very different properties and behaviors and dynamics at different scales. So looking only at the global scale or the micro scale does not really give us a full picture. And clouds are important just because of how much effect they have on our radiative budget, whether a certain region of the world is cooling down or warming up, just because of the atmospheric effects. So now, what can we do with Sentinel-2, a satellite that just covers a small part of the world every 5 days? And it has 10-meter resolution, but it doesn't really have the instrumentation that you would expect from a satellite that's been designed for monitoring clouds. Well, we have to get creative, right? So one of the things we've done here, and it was actually the first algorithm implemented by Alistair very early on into the project, also inspired by a paper from a few years ago that basically takes advantage of the fact that every Sentinel-2 band gets captured at a slightly different time. So with that, you do get a sort of a parallax effect, right? If the cloud was just lying on the surface, there would be no parallax effect, right? But if you lift it up, if you move the satellite around the cloud, you will get a different perspective from each band, right? And we can use that to our advantage to estimate the shift for the same cloud between different bands. And if we estimate the shift, we can actually analytically estimate the height of a given cloud. And we have to be specific here, right? We're looking at the cloud tops. Clouds often have many layers, very complex structures, and all we see from Sentinel-2 mostly are the cloud tops, so that's what we can estimate. There are some techniques where we're exploring multi-layer clouds, but in general, it's a major obstacle. So we're focusing on cloud tops, but already we get an idea of the cloud height, which allows us to have an idea about their effect on whether they're cooling or warming, right? If they're very, very low, it means that they are actually cooling, like the cumulus cloud that give you shade on a beach on a sunny day, right? But if they're very high up, they are the types of clouds that trap heat, right? So knowing how high your cloud is, you know a little bit more about their effect on whether they're cooling or warming the Earth that's below it. We've done some validation. We've actually validated at small scale for now by looking at the cloud shadows and comparing that to the estimations of the algorithm. You can learn more about clouds decoded on that QR code. Or if you just go to our website, you will learn more, because there are other properties that we're trying to estimate from Sentinel-2, but this is just one of the early success examples of what could be extracted from Sentinel-2 for understanding clouds a little better. Okay, so one of the solutions that we try to live by is staring at the clouds. Or more generally, looking at the same data through new lenses, right? So again, we have tens of petabytes of data that's available to everyone, that's funded by everyone publicly, that we might not be taking full advantage of, right? So there will be new instruments coming out in the next couple of years, and they're all very exciting. But we have all of that sitting in the archive and possibly not being taken full advantage of. Okay, any other solutions? Starting a cooperative research lab. So this is an image from our launch party, and now I can cover what Asterisk Labs is about. And Asterisk Labs is basically a result of Clouds Decoded being funded about a year ago by ARIA, Advanced Research and Invention Agency in the UK. And winning a project that gives us a significant runway also allowed us to build something that we always felt like we wanted to build. So all three of us knew that we wanted to find some place that allows us to conduct research for many years, maybe finding alternative routes to switching between postdocs or trying the usual routes that everyone's familiar with. It's just really hard to find a place where you can stay committed to the research and you can maybe build a little bit of stability within your workplace and focus exclusively on research and not on the commercial sustainability, right? So that's what Asterisk Labs is, really. It's a cooperative model where every scientist owns equal stake in the lab. We are not for profit, so we don't have shares or we cannot accept external investments. And every single scientist on board has the same influence over the decisions that we make at Asterisk. Now, as soon as we founded Asterisk, we started asking ourselves, like, okay, what are the kind of cool things to say about Asterisk? What is our mission? So, first of all, we call that Earth Data Commons. All of the information that we gather as humans about our planet, we consider Earth Data Commons, especially if they are available to everyone and give us some information about what's going on Earth. We want to make these easier to access and understand, whatever that means, by collaborating with different projects or by designing tools of our own. We also want to find more narratives like Clouds Decoded, where we look at existing data in a brand new way, and we find new applications of the data that's already there without having to invest in a whole new ground segment. And then we want to inspire others, like Asterisk Labs has nothing to gain by becoming the biggest research lab that is out there. We do want to create a blueprint for other organizations where scientists can form other types of structures where they can fully commit to science and find a place where they can sustainably operate within the research domain for a number of years. So what now? Okay, I will start wrapping up with some of the directions that we have for the next couple of months at least. So on the access to Earth Data Commons front, we are currently working on the AI vision for Copernicus, contracted by the European Space Agency Copernicus office. We can actually take your input. So if you scan this QR code and fill in a Google form, you can tell us everything that you love and hate about working with the Copernicus data. And the idea here is to give a set of recommendations to people responsible for the future of Copernicus about how Copernicus can make it easier for people to develop AI on top of their data, but also how the future landscape of AI models and techniques might look like down the line, and how that might affect the way we interact with Copernicus data, right? We've had some discussions about embeddings and retrieval at a large scale. There's a lot of that being developed right now that might make the future very exciting, but also we want to make sure that the future of the program is designed with this in mind, at least to some degree. So you can also obviously go to you can contact us, and we can send you that form as well. We only have about a week or two before we have to wrap things up. So if you want your voice heard, you better hurry up. We also recently proposed TACO as an idea to the ESA Lab Ideas call. The QR code is the documentation of the project that's basically work in progress. It's developed by Cesar Ibar from the University of Valencia. But it also addresses one of the main challenges with Major Tom. And right now, Major Tom is delivered as very large parquets with the byte streams from the geotiffs, for those who are familiar with data formats, just because of how much easier it was to upload that way to Hugging Face. We worked with the Hugging Face team to make sure that we can deliver this reliably at the scale of 70 terabytes of data. But TACO actually allows us to do a little bit better in terms of accessing random subsets of the data and also optimizing the throughput from the drives or from the cloud to your GPU. So if you want to train on Major Tom in the future much more efficiently, you can follow the developments of TACO. And there's a few prototypes that give us fairly high confidence that it can work very well. Okay, a new phase of science. So another thing we want to do is actually focus on research, but also focusing on connecting that research to people who don't normally interact with researchers, right? So in the context of Clouds Decoded, we work quite a lot with the Cloud Appreciation Society. It's a society with over 60,000 members worldwide, and it's just people who get excited or too excited about clouds. There is a Cloud Spotter app, which allows you to capture clouds, and there's always a discussion about these captures through the app. There's people rating clouds and basically having discussions about which type of cloud that is, and there's actually a very rich source of data that's on the back end of that app. So if you're interested, that is a very fun resource. And we've recently also hosted a Clouds and Climate fireside chat with one of our collaborating scientists, Ed, and also Gavin, the member number 1 of the Cloud Appreciation Society. You can watch that on YouTube, and it's in a fairly accessible format, and it's very fun to listen to. And it was a real honor to have them come on and produce that episode for them. What else? There's a lot of discussions about alternative research research structures that we can explore the next couple of years. And to us, it's really interesting because obviously one of the major challenges for Asterisk Labs is to find the right dynamics for funding our research, making it sustainable, finding the right trade-off between our commitment to open science, keeping everything open, and doing research that generally we feel should be done, and also being a sustainable workplace for our scientists. So if you're interested in different scientific models, and there's a lot of interesting history covered on the FreakTakes Substack, it's a very interesting topic to explore as well. Finally, same data, new eyes. We are currently preparing a new mechanism for growing Asterisk Labs. So obviously, a major decision for hiring a new scientist at Asterisk is a major decision for us, right? Because we're all collectively responsible for raising funding, and it works slightly differently from this individualistic approach where you have your project, you do your project, and then you need to personally look for something new to do. We actually all share responsibility for making Asterisk sustainable. And right now we're working, and we're getting very close to finding a way to fund this, where we basically collaborate with potential scientists who have these ideas for looking at the same data with new eyes and actually joining us as a partner scientist, right? So we are trying to fund a program that allows us to pay them for their time to produce a proposal, a funding proposal that they have the full IP rights for, and work with us to hopefully start and spin out a new research project within Asterisk Labs. So if you're interested, you can always get in touch with us, and hopefully we'll have more to share in the next couple of weeks. So again, I will repeat the last three. I will repeat one more time the solutions that we have and the interesting directions that are very relevant for us on Asterisk. And I will simplify this to the message that just sticks very easily, and it's stare at the clouds. Looking at the same data in new light, looking at the data that's normally discarded, that's considered noise or distortions, in a way that allows us to find new uses and find new value in the data that's already out there, is something we really try to spend a lot of our energy on. I think that's about it, so I will close with that, and if you have any questions, I will be very happy to answer them. Thank you.
Thank you so much, Miko. It was such a nice presentation, solution-based, inspiring and encouraging, especially for postdocs here, I think. So we have some question time. Any questions from the crowd? Don't be shy.
Thank you for the presentation. I have a bit of a question regarding, you said that Major DOM allows you to easily get started and work on data, and I see this. And then one of the other pain points when you work on remote sensing data is that, say you've trained a model, now you want to deploy this large scale to make a map. Do you foresee limitations to using Major DOM for that? Like, do you have do you handle radiometric shifts between the tiles, all these things? Or do you think of working on something to help people to deploy their models globally and make maps regularly without having to spend $10,000 in server?
I don't think that's solved yet. And Major DOM, I mean, the data sets that are within Major DOM. Major DOM in general is a framework for producing new data sets. And we've produced a few data sets that we refer to as Major DOM as instances of those. So the choices that we've made were very much oriented towards pre-training, right? So for every single location within the current Major DOM data sets, you have a random sample that's mostly cloud-free from the entire Sentinel-2 archive, right? So it's not very suitable for building maps where you might want to have more or less the same period for nearby locations. And that basically boils down to I mean, we've had these discussions very early on, because we also had ideas for producing like yearly Major DOMs where we try to get the same season or so, but it's a substantial effort. It's an effort that took us 4 or 5 months from within ESA with full access to the Copernicus archives, right? That was a single sample. We decided to make it a pre-training data set. It would be very fun to look, and I am aware of a few potential projects, not necessarily with Asterisk involved even, that might also add some additional expansions that, I mean, obviously a lot of people ask about time series support, and if we had time series Major DOM, we could have something that's more similar to a data set that you could deploy on and build global maps. So maybe, I don't have a clear answer here. And regarding other obstacles like radiometric calibration and other inconsistencies, that's not solved either. I mean, Major DOM is a very quick hack that just allows you to align people who independently produce open data together, right? And they might make different decisions. I mean, Major DOM does not force you to use any specific projection, right? We normally use Sentinel-2 projection for that specific location, right? And even Sentinel-2 for the same location might have different projections if you are close to UTM zone border, right? So we try to make it fairly flexible, where the dataset producer or curator decides what projection they want to use and how they want to deliver their data. So hopefully it's a format that's open enough that allows people for some flexibility. So if there is someone who wants to solve that problem, they can do that. But it's definitely a substantial piece of work that needs to be done. Thanks.
Any more questions? Maybe a quick one. Okay, I bet people will approach you and have more personal questions. So one more round of applause for Miko. Thank you.